The missing piece in our puzzle is knowing whether or not the amount of irrigation we're applying to each plot is the ideal ratio relative to ET. The obvious solution is to monitor the status of the plant itself. Every plant has a daily cycle. During the day, sunlight activates the leaves for the process of photosynthesis, which manufactures the carbohydrate building blocks needed to produce fruit. The stomata of the leaves open to let carbon dioxide in, but these openings also allow water to be lost from the leaf tissue. The size of the stomata opening is determined by the amount of water in its guard cells. The more water, the larger the opening. Less water means a smaller opening. It's the same water holding the stomata open that's lost through it being open. Losing water isn't a bad thing, as long as the plant can maintain the supply of water to its leaves. Then photosynthesis will continue, and the plant maintains growth and fruit production. Water in the soil enters the root system and travels to the leaves through the trunk. If the plant is losing more water through transpiration than it can take up through its root system, the trunk shrinks as these water pathways are depleted. For most crops, under most conditions, they inevitably lose more water than what they take up during the day, which results in a natural contraction of the trunk. At night, though, photosynthesis stops. The stomata in the leaves close and the plant stops transpiring. But the plant keeps drawing water up through its roots, and because it's no longer losing water through its leaves, it replenishes its store in the trunk and branches, resulting in a natural expansion of the trunk. At Phytech, we deploy plant sensors that monitor the microscopic changes in the trunk diameter on an hourly basis. Over the course of a 24-hour period, we graph this contraction and expansion of the trunk. Our sensors can detect changes as small as 5/1000ths of a millimeter, or 1/20th of a human hair, and they're called Dendrometers. They've been around for decades, but they were typically only used by plant scientists because of the complexity and time taken to interpret the graph. To make the data fast and simple for growers, we developed algorithms to automatically interpret the dendrometer graphs and convert it into a simple color to give an indication of plant stress, like a traffic light signal on each plot. Red is for stress that significantly affects yield. Orange for stress that slightly affects yield. Yellow for stress that's on the border of affecting yield. Light green for no stress, and dark green for a saturated crop that has more water available to it than it needs. Every species, and even variety, has a different stress signature. An acceptable pattern for Hass avocado could represent significant stress in navel oranges or sugarcane. Our crop-specific algorithms are tuned to guide you using colors to achieve maximum production. There are lots of factors and measurements that make up each algorithm, but a common factor is maximum daily shrinkage, or MDS. If we think of the plant sensor as a fuel tank gauge, measuring the store of water in the trunk, then MDS represents the amount of water used during the day, answering the question, how much of the water stored in the tree did it use? To understand why this factor is important, we need to look again at how the water is lost through transpiration. Although it's safe to use some of the water stored in the trunk, if it goes past a certain point, the stomata start to close. That reduces photosynthesis and the production of sugars or carbohydrates. It's a gradual process and a relatively linear relationship between the amount of water lost from the trunk and the reduction in photosynthesis. The same water that keeps the stomata open is what holds the leaf stems up so they face the sun. So when the water in the trunk is almost completely exhausted, that's when we typically see the visual signs of plant stress, leaf wilt. The Phytech algorithm, though, is calibrated to plant productivity, not visual signs of stress. That's why the trigger point for the red plant status is well before you can see any change in the plant with your eyes. Just like you expect the fuel light in your car to warn you before you run out of fuel, not afterwards. The color indicator shows you the plant's worst state in any given part of that day. You might spend most of the day in the green and yellow zones, but just 1 hour in the orange zone will trigger the orange alert for that day. The rate at which your crop's water store is depleted depends on supply and demand. Supply is based on the water available to the active roots of the plant and their capacity to absorb it. If there's less water available, or it's available to less of the roots, then supply is reduced and your tank level gauge falls faster. You have some control over the supply by adjusting the frequency and duration of the irrigation. Demand is more complicated. The most obvious and variable component that affects demand is the climate, because transpiration increases with temperature, wind, and radiation, but decreases with relative humidity. The components affecting demand that vary less over the short term are phenological stage and fruit load. And another component that affects demand is external manipulation, things like pruning, fruit thinning, or applying covers in table grapes. Sometimes it's not possible to avoid stress. A fruit or nut tree carrying reasonable yield will be stressed on a very hot, windy day, no matter what soil type it grows in or how much irrigation was applied. The objective is to avoid the stress you can control. Another common factor included in our automated analysis, especially for tree crops, is daily growth. If MDS was the measure of the fuel level, then growth is the measure of whether the tank refilled by the start of the next day. We know that the amount of water in the plant's tank is relative to its productivity. So if it can't completely refill its tank each night, then we risk starting a new day with reduced productivity or entering that state of reduced productivity sooner. So what typically prevents the tank from refilling at the end of each day? The amount of water available to the roots. If there's ample water available to the roots, the rate of recovery is relative to the amount of water in the tank. A tree that's lost a lot of its water reserve is like a thirsty vacuum. But as it refills, the rate of recovery reduces. If the plant fails to recover each night, especially over multiple days, then a colour alert of yellow, orange, or red may be applied, depending on the severity. So when you see an orange or red status, you need to investigate a little further to understand its cause. Is it because the tree used a lot of its water reserves? Or because it didn't refill those reserves? Or both? The most common reason for a plant to reduce its productivity is lack of water. Too much water, though, can also trigger plant shock and lead to reduced productivity. But the stress signature for too much water looks different. If the contraction is too large, we know productivity is affected by lack of water. If there's no contraction, it's an indicator that there's too much water available to the plant based on its current demand. We display the dark green colour when the crop-specific criteria for oversaturation is met. It's an indication that there might be an opportunity to reduce irrigation and save water whilst also increasing productivity. You can see the criteria we use to display the light green daily plant status are very specific and difficult to fake. That means light green truly indicates that your plants are operating at their optimum potential. Now, that daily status of the plant gives us the final piece of our puzzle, which means we can close the loop and find the ideal ratio between ET and irrigation applied. In the next video, we'll see how this ratio can help us make future irrigation decisions.